In this video, we try to know about the 3NF and BCNF. So before going to this video, you watch the previous videos of mine of 2NF and how to find the candidate key are given in the those links are given in the description box. If you find that it is very easy to solve the 3NF and BCNF. So let's start. So the first one is 3NF. So 3NF means it should be in the 2NF first of all, the first most condition, and the second condition is very important. With the help of this we can able to find whether it is 3NF or not. If x gives rise to y, x should be the super key or y must be a prime attribute. So what is a prime attribute? The part of a candidate keys. So what are the elements are present in the candidate keys is nothing but a prime attribute. Or if you want a clear definition, the attributes which are there in the candidate keys are said to be the prime attributes. That's it. Let's take an example. If you have a table of A, B, C, D, E, F and you are given some functional dependencies and the aim is to convert it into the 3NF. So the first and foremost thing is that first find candidate keys and find prime attributes. So let's try to find what is the candidate keys. So here is given the ABC. So how you get the ABC is very simple. First of all, you need to mark the right side elements C, D and E and F in the table. So C, D, E, F. So what are the elements left over present here? A, B and G. So find closure of it. If you get all the attributes in the table, then ABG is said to be the candidate key. So here you get all the attributes in the table, so ABG is said to be the candidate key. So we need not to go into the further, there is only one candidate key, that is ABG. So you have written the candidate key as ABG and the prime attributes as A, B, A, comma, B, comma, G. So that now we need to check the second so the table is already in the 2NF and we need to convert into the we need to check the second condition, whether X is a super key or Y is a prime attribute. So let's start with the first one. AB gives rise to C. So AB is not a super key or C is not a prime attribute because only the ABG are the prime attributes. So in this situation we need to find the left side of the functional dependency, that is AB. Find the closure of AB. So if you find the closure of AB, you will get the A, B, C, D, E, F. So what are, except AB, what are the elements are present here? C, D, E, F. So delete those elements into the previous table and include this AB and write into a new table, so that you will get A, B, C, D, E, F, and the other table is ABG. So the leftover elements in the previous table. So two tables you have got. Let's wait. Yes. And you need to write all the functional dependencies coming under this. What are the comes under the A, B, C, D, E, F? You will get the AB gives rise to C, and C gives rise to D, and D gives rise to E. D gives rise to E. That's it. So D gives rise to E. Is there any more? And B gives rise to F also. So B gives rise to F. So those all comes under the first table. So in the second table you didn't get anything, but still these functional dependencies all come into the first table. And let's check the second one. C gives rise to E. So now you find the primary candidate key of this table. You will get the AB as a candidate key. Now the candidate key is AB, because you can see that AB gives rise to C, and with the help of C you are getting the D, with the help of D you are getting the E, and with the help of B you are getting the F. So AB is the candidate key. Now take the second one. What is the second one? C gives rise to D. Whether C is a candidate key, we need to check. The first condition here satisfies because AB is a candidate key, no problem, because right side. The left side is C gives rise to. So C is not a super key and D is not a prime attribute. So find the C plus. If you find C plus, you will get the C, D and E. So similarly, in the previous table you try to delete the D and E and make into the new table as CDE and ABCF and ABG. It is as simple as that. And the next one is, now you need to check, you need to find the candidate keys into this table. So what are the candidate keys are there? So let's try to find. So here in CDE table, we need to find the table in the CDE. Let's make this some bigger so it will some clarity there. Yeah, so in the CDE table, what are the functional dependencies are there? C gives rise to D comes under this, and D gives rise to E. So both are coming in this table. And what are the tables, what are the functional dependencies are present in this table? It is AB gives rise to C and B gives rise to F. B gives rise to F. So what are the candidate keys in this table? Wait, Control Z. Yeah, candidate keys in this table. So it is very simple, because candidate key is C, because with the help of C you are getting the D, with the help of D you are getting the E. So there is only one candidate key, that is C. And now check whether it is in the CNF or not. And you need, so the C gives rise to E, so C is said to be the candidate key, and so it is a super key. So it satisfies the property. Then what about the second condition? D gives rise to E, whether it is satisfying or not. Because D gives rise to E, D is not a super key, and E is not a prime attribute here. So what we need to do, divide into the another table. So find D plus. So now find D plus. So what you will get? You will get the D comma E. So make into a separate table such that the sub tables are CD or DE. That's it. It is very simple. You just find the closure. You need delete the D and E, make into a new table, and delete E from the previous table. That's it. So now write the functional dependencies present here. The first functional dependencies in this table is C gives rise to D, and here D gives rise to E. Now find the candidate keys in the both the tables. Here candidate key is C, because it is a super key, so it is in 3NF, and D is a candidate key in this table, so it is also it is in 3NF. So both are in 3NF. Now check here. AB gives rise to C is whether in the 2NF or not. Here AB is a candidate key, so AB is a super key, so we need not to be worried about that. So but B is not a super key, and F is not a prime attribute. So here problem occurs. So whenever the problem occurs, you need to find the closure of that. So find the closure of B plus. So you will get the B comma F. That's it. So make into the separate table in such a way that delete F from the previous table and add BF into a new table. So the tables here arise are BF or and what are the other table you get? If you delete the F from the previous table, ABC. So ABC. So two tables are, if you get the two tables here. So what are the functional dependencies which comes under the BF? So B gives rise to F comes under this. B gives rise to F, that's fine. And here you will get that AB gives rise to C. Here B is the candidate key and B is a super key, so no problem, it is in 3NF. AB here in this table, it is a super key, so here also no problem because AB is a super key. So all the attributes are satisfied in the 3NF property. Therefore the functional dependencies is said to be in the 3NF. So how many tables you get that? You just mark it. The first table is CD and the second table is DE and the third one is ABCF. Oh, here mistaken. Yeah, ABCF, and the last one is ABG. So here not ABCF, here ABC and BF. That's it. So in this way you need to convert into the 3NF. So the 3NF is looks very some lengthy, but it is very simple. If you find the candidate keys and if you find the all the divide into the tables, that's it. And the BCNF is also same, but you have only one condition. You don't have other condition, that is the y need not to be a prime attribute. So you need to have only one condition, that is x must be a super key. That's it. So similar process, so need not to be explained again because it is very simple. But now try to check the previous year's gate questions on the BCNF, 3NF and 2NF, and basically normalization and keys. Let's start with that. Yeah, this is a gate question asked in 2014. So what is the maximum number of super keys for a relation schema R of a given table E, F, G, H, with E is a key? So here, what is a super key? It should be the combination of primary key with any other attributes, and the primary key itself is also a super key. So the first here he given that E is a key, so therefore E is one of the super key, and with the help of E, if you can find the two attributes, EF and EG and EH. So here 4 are you get that, and with the help of 3, now make the 3 sets, EFH. Let's go in the order, EFG, EFH, EGH, and you got the fourths, EFGH. So how many did you get? You get the 3, 4, 5, 6, 7, 8. So here you have the 8 keys. 8 keys are present, 3, 4, 5, 6, 7, 8. So that's it. It is very simple. The answer is 8. Maximum number of super keys for this relation is 8. So let's see the next question. So you have given a schema, that is given a table of R with these attributes, and these are the functional dependencies, and what is the key for R? So it is asking that whether it is we need to find the candidate key. So options are given, EF, EFZ. So the simple way is just find EF and check whether the all attributes you are deriving or not. So let's try to solve that. Now find the EF closure of E and F. So you will get E comma F, and with the help of E comma F you are deriving the G. So you are deriving the G, you are deriving the G, and with the help of F you are deriving the I comma J. Okay, with the help of E, H is not available, so leave it, and K is also not available, L is also not available. So EF is not a candidate key. So let's check the next option, E comma F comma H. So with the help of E comma F comma H, yeah, with the help of E comma F you are deriving the G, and with the help of F you have deriving the I comma J, and you have E and H. Yeah, E and H is available, so include K and L. So K comma L, and with the help of K you can derive the M, and with the help of L is also present, so you can derive the N. So here all the attributes are derived, so this is a key. And if you find that EFJKL, it is also you will get the key, but here it is asking that key, so it is not mentioning whether it is super key or primary key. So there are the two options are available, so B and C are both correct. But if we ask only for primary key, then primary key or candidate key, then option B is right. If we ask a super key, then both B and C are right. In this way we need to find that. Yes, let's see next question. So here it is asking that how many candidate keys are available for this relation, and this is asked in the GATE CS 2013. So let's try to find that. The first thing you need to write here, wait, Yeah, the first thing you need to write is all the attributes which are present. Yeah, here you have a comma b comma c comma d comma e and f g h. So up to a to h are there, and you first of all you need to find that what are the elements which are present in the right side. So what are the elements present in the right side? You have g, so here mark g, and you have bc, so mark b and c, and you have c f h, so mark c and f and h, and you have a e g, so a e and g. So what are the remaining elements left over? You have only, let's take a new table. Here you try to find the candidate closure of d plus, then you will get only the d, because with the help of d there is no attributes you can derive, so only d, so it is not a candidate key. So make a combination with the help of the d with all the other attributes. So what are the combinations are there? AD, BD, CD, DE and DF and DG and DH. Try to find the closure of all those. So if you find the closure, then here you will get the all attributes, and so it is a candidate key, and this is also a candidate key. So two candidate keys are there, and here two candidate keys. So whether we need to stop? No, because some of them are not the candidate key. So try to find those combinations. So what are the leftover? CD, DG and DH. So now try to find the combinations of all those. So here, even if you are getting the combinations of the three combinations, if you check that CDG, CF, CHD and GHD, so all those are not deriving the entire attributes, so these are not a candidate keys. And if you take the combination of the four, if you take CDGH, so even though you are not getting, so here we can stop because there are no other elements. We need to check so that we can have some combinations. So the answer is 4. 1 2 3 4. So in this way we need to find that how candidate keys. So the answer is 4. So let's check next one. Yeah, it is also a similar question. It is asked in 2005. So find the what are the candidate keys of R. So here you can have one candidate key or more than one candidate key. So let's try to find those. So first of all, make all those attributes which are present: A, B, C, D, E and H. The first important thing is that which are present in the right side, so mark all those elements. So yeah, here you have, let's take bread. Yeah, here you have B and D and C and A, so mark all those. So B and A are there, and C, D are there. Yeah, B, C, D, A. So EH is not there, so EH must be in the candidate key. So let's try to find the closure of EH, so whether we find that or not. So closure of EH, with the help of EH you are getting the E and H. So with the help of E you can derive the C, and with the help of C you can derive nothing. So make a combination of all with the help of the E and G. So if you find the candidate key, you find the closure of all the combinations of AEH and BEH and CEH and DEH, then you are getting the 3 candidate keys which can able to derive all the attributes. So those are nothing but AEH and BEH and DEH. So whether you can stop or not, there is one element which is not satisfying the property. So with the one we cannot form more than one combination. So here we can stop. The answer is 3, and those are nothing but AEH, BEH and DEH. So let's see next question. Yeah, that's it. Thank you.